Hello, this is the lecture for section 1.4, composition of functions. Now, what does it mean to compose functions? When we compose functions, what we do is the output of one function becomes the input of another, or a composite function is a function that's created by using the output of one function as the input of another. The notation that we use to describe composite functions is f of g of x. F of g of x, this inside function, g of x, the output of this inside function becomes the input to the outside function, to f. There's a symbol for composite functions. It's a little floating circle like that. So this f of g of x would read, when the floating circle is used, this reads f composed with g of x. All right. So let's look at some examples. If we are composing functions, in this first example here, we want to compose f and g. So we want the output of g to become the input of f. All right. So what we would need to do before we could find f of g of 0, this is for a specific input, 0, we need to find what g of 0 is first. Right? So let's see if we can find g of 0. Let's see. G of 0 is going to be 0 squared minus 3 or negative 3. All right? Once we know that value, then we can find f of g of 0, because what we're going to find here is f of 3, since 3 is the output of g. All right, what is f of 3? Well, let's see, f of 3 is going to be 2 times 3 minus 1, or 6 minus 1, that's 5. All right, so f of g of 0 is equal to 5. I might also say f composed with g at 0 equals 5. Okay? These two statements would say the same thing, just using different symbols. All right, look at the next example, g of f of 0. Is this going to be the same value? No. This time, we want to evaluate f of 0, whatever that value is, whatever the output of f is when the input is 0, is going to be the input that we feed into g, right? Or whatever f of 0 is, whatever value that is, that's what we're going to substitute in for x and g, right? So we would need f of 0 first. Let's see if we can find f of 0. I'll put that up here maybe. F of 0 is simply 2 times 0 minus 1, or negative 1, all right? So f of 0 is negative 1. So to find g of f of 0, what we want to do is we want to find g of negative 1. All right, since f of 0 is equal to negative 1. And g of negative 1, we haven't found that yet. Here, we'll just do it right here. G of negative 1, we're going to put negative 1 into the function g for x. It's going to become the input, right? So that's going to be negative 1 squared minus 3. Okay? Negative 1 squared would be 1 minus 3, so that'll end up being negative 2. Okay. How about f of 0, or f composed with f at x equals 0? All right, well, we need f of 0 first. We already found f of 0. F of 0 is negative 1. F of 0 is negative 1. So to find f of 0, we want to find f of negative 1. Okay, since f of 0, we already know, is equal to negative 1. We found it up there. All right, so what is f of negative 1? Let's see, we'll put negative 1 into f. So that's going to be 2 times negative 1 minus 1. 2 times negative 1 is negative 2. Negative 2 minus 1 is negative 3. Okay, g of 0. No rocket science here. We need to find g of 0 first, which we already have. We found it up here in purple. G of 0 is negative 3. So g of 0 is going to be g of negative 3. right? Or we want to evaluate the function g at x equals -3. So what is g of -3? Did we find that yet? Nope. So let's find it. G of -3 is going to equal -3 squared minus 3. Well, that's 9 minus 3, or 6. Okay. One last example here. F of g of -1. And we found g of -1. Yeah, we did find g of -1. It was over here. G of -1 is -2. Right? So to find f of g of -1, what we want to find is f of -2. Okay, so f of -2 doesn't look like anything we found, so let's evaluate that. We'll evaluate f at x equals -2. That's going to be 2 times -2 minus 1. Right? That'd be -4 minus 1, or -5. Okay? So evaluating composite functions is not too bad. We just find the output of the inside function, and it becomes the input to the outside function, right? If we were to draw a diagram of composite functions, it would look like this. Say we were doing f of g of 0, right? If we wanted to draw maybe a diagram that represented f of g of 0, it would look like this. We would have the function g. What if say the function g is something like this? Okay, g is defined as x squared minus 3. Okay, and it's going to take 0 as its input, right? So 0 feeds into g. What does it spit out? What is g of 0? We found that g of 0 was -3, so it spits out -3. Okay, and then -3 will become the input to that outside function, right? To that outside function. -3 is going to become the input to f, right? It's going to go in there. F is defined as 2x minus 1. Okay, so -3, we feed that into the function 2x minus 1, right? And we multiply that input by 2, so that's a negative. Oh, did I do this wrong? Oh, yeah. 3 times 2, 6, and then we subtract 1 from it, that's 5. So 5 then is the output. Right? So visually, as a diagram, what might be happening in a composite function in f of g of 0. We have to evaluate the inside part first. Order of operations tells us to do that too, right? Do what's in the parentheses first. Then, once we know that value, we can feed it into that outside value. All right. Let's take another look at another example evaluating composite functions. Here we don't know. We don't know the rule of the function, right? Or we don't know its formula. Here we knew the rule. We knew the formula, x squared minus 3 for g, 2x minus 1 for f. We don't know it here, but that's okay. As long as we know inputs and outputs, we're good to go. All right. So x, that's our input, right? There's a column for x. When we feed this value of x into f of x, here's the output that we see. So when we feed 0 into f of x, the output is -3. When we feed 0 into g of x, the output is going to be 5, right? So on and so forth. Feed 1 into f of x, we get 4. Feed 4 into g of x, the output would be 2, right? So using these table of values, these inputs and outputs, can we find f of g of 0 for this example? Yeah, we just need to know what g of 0 is first, right? So what is g of 0? When x is 0, okay, here's our x column. When x is 0, what is g? Go over here to the g column. It's 5, right? When x is 0, g, the output, g is 5. So what we're really looking for here then is f of 5. All right, let's see if we can find f of 5. When x is 5, I'm going to do that one in red. When x is 5, let's go down here to 5. When x is 5, what is f? It's 1. When x is 5, f is 1. So that means f of 5 is going to equal 1. Okay? Look at the next example. Here we're going to do f of g of 1. F of g of 1. So here we need to know what g of 1 is first, since that's the inside function, right? We need to evaluate that first. What is g of 1? All right, well, when x is 1, we're in the second row of this table. We go over to the g column, and we see that g of 1 is 0, right? So then what we're going to look for here is f of g of 1, or f of 0. F of 0. All right, so what is f of 0? We have to go to the 0 row in the table, or when x equals 0. When x equals 0, we need to find out what f is, or what the output is. When x is 0, the output is, oh look, we're back here at 5 again. We already did f of 0 somewhere, didn't we? Well, that's g of 0. I'm so sorry. F of 0 is negative 3. F of 0 is negative 3. I just looked at the wrong column. So f of 0 is negative 3. So f of g of 1 is negative 3. Woo, it's confusing. Okay, g of f of 2, we need f of 2 first. We need f of 2 first. Let's see if we can find f of 2. Well, there's where x is 2. What is f when x is 2? It's 0. Okay, so g of f of 2 is going to be g of 0. All right, and what is g of 0? Well, back up here to the 0 row in the table, and g of 0 is over here at 5. G of 0 is equal to 5. Okay. One more, f of 4. Have we found f of 4 yet? No, let's see. Well, let's find what f of 4 is. I'm going to call it f of 4. Let's see. We'll go over here to when x is 4. We're in this second to last row in the table. What is f when x is 4? It's 2. Okay? So f of 4 is simply going to be f of 2. Yeah, let's go up there to the 2, go up here to the 2 row where x is 2. And what is f? 0. F of 2 is 0. Okay? Ooh, these tables always get me. They're like complicated, but the concept here is important. It's the output of that inside function becomes the input of the outside function. All right? Let's look at an example of evaluating composite functions when we just have the graph. When we just have the graph, all right? So here we have a graph, f of x and g of x. Here, f of x is the red one. Yeah, I'll go over there in red. Okay, f of x is the red graph. Okay, it's a piecewise function, isn't it? And then g of x, well, g of x can be this blue or teal colored graph. So there's g of x. Blue. All right, so from the graph, can we determine f of g of negative 3? Sure, we need to find g of negative 3 first. Okay, so where is g of negative 3? The x is negative 3, the input is negative 3. So let's go here. Here it's hard to see, so let me write over it. There's negative 3. On the graph of g, where is x negative 3? Let's do colors here. On the graph of g, x is negative 3 right here. Okay, so the coordinates of that point then are negative 3, 2. Negative 3, 2. The x is negative 3, of course the y is 2. Okay, so this means that g of negative 3 equals what? It equals 2. Okay, so f of g of negative 3 is really f of 2 when we evaluate that inside function. Okay, so what's f of 2? Well, let's look at that. We got to go over to the f graph now, and we're going to find where x is 2. Small labeling again, but there it is. There's where x is 2. Okay, so that corresponds to, we want f now. So that's going to correspond to this point down here. All right, this point down here. Maybe we'll make him, I don't like that color. I'm switching my color here. We'll make that pink, right? So the coordinates of that point then are 2, and the y is -1. Kind of hard to see some of these values, but there's a -1 right there. So, so we now know what f of -2 is. F of -2 is the y-coordinate of the point, right? It's -1. Oh, I did f of 2, not f of -2, didn't I? Let's just change it. We'll just change it, okay? We're going to call that f of +2. And we're just going to change the example. So f of +2 is -1. So now what we want to find is g of -1. G of -1. We're doing f of +2. I just changed it since I looked at the wrong point. Okay, g of -1. All right, now we have to look at the g graph, and we have to find where x is -1, right? That's our input. X is -1 right here is -1. The graph of g, that's the teal kind of graph. So the point we're looking at is right there. The coordinates of that point are going to be -1, 0. Let's write that in. There's a different color. The coordinates are -1, 0. Okay, the y is 0 and the x is -1. So that means g of -1 is what? Simply 0. So g of f of 2, g of f of 2 is 0. Make sense? How about f of -1? All right. Well, here's -1 on the graph right there. Here's the graph of f. It's the red one, so it's this point here that we want. Maybe we'll put him in red. The coordinates of this point are -1, 1, the one right there. Right. So that means what? F of -1 is equal to 1. So what we want to find here now is f of 1. What's f of 1? Well, let's see, where's our graph? We're still in the graph of f. So we're still on our red graph. When x is 1, there's that 1 right there. We're looking at this point here. Looking at this point, the coordinates of that point are 1, 1. Right, 1, 1. Oh, do I have a different color I can use? How about this one? 1, 1. All right, so that means f of 1 equals 1, right? So f of -1 is going to be 1. All right, one more, g of 0. Okay, we're back on the g graph now, our teal graph. X is 0, there's the origin right there. So the point we want to graph is this point. The coordinates of this point are 0, -1. So let's put that one in. 0, -1. All right. So g of 0 is what? It's -1. -1. So we want to find now g of -1. Well, let's see, where's -1 on our graph of g? -1 on our graph of g is here. Oh, that's that green point, right? And g is -1, y of 0. So g of -1, same as up there, is equal to 0. All right? It's complicated. Just got to kind of think about exactly what does a composite function mean. What does it mean? It means that the output of that inside function becomes the input of the outside function. All right. What if we need to find the formula for a composite function? What if we want to compose one function into another, okay? And we don't really want to find it for a specific input. We don't want to evaluate it. We just want to find the new formula. We want to find the algebraic representation of a composite function. So how do we do that? Well, we do that by taking that whole entire inside function and shoving it in everywhere the outside function is expecting an input. Right? So f of g of x means we're going to take all of g of x, so the formula for g of x, and we're going to put it into f of x where it's expecting an input, where it's expecting an x. Right? So it's going to go in here. To have x squared, that's going to be 1 over x plus 2 squared. It's also going to get substituted in there for that x. Right? So let's see if we can write that. F of g of x, okay, Algebraic representation is going to be the input squared, or 1 over x plus 2 squared. Okay. And then minus 3 times the input, or 3 times g of x, 1 over x plus 2. Right? If I were just to write that very symbolically, this would be g of x squared minus 3 times g of x. Okay, because g of x is this input, right? This is what I'm putting in there for the input. All right, now there it is. That's kind of messy, so we might want to simplify that a little bit. Let's see if we can find what 1 over x plus 2 squared is. Let's do it up here. Make some space. 1 over x plus 2 times 1 over x plus 2. Right, that's going to be 1 over x times 1 over x, or 1 over x squared, plus 2 over x plus another 2 over x. That'll be plus 4 over x, right? And plus 2 times 2, or plus 4. All right, so there's that first part. 1 over x squared plus 4 over x plus 4. Now we're going to subtract from that 3 times 1 over x plus 2. Let's just go ahead and distribute that 3 right now. So that'd be negative 3 over x minus 3 times 2, or minus 6. Okay. See, we can combine some terms here, can't we? There's only one x squared term, so we'll leave that 1 over x squared. But look, here I've got a 4 over x minus a 3 over x. That ends up being a positive 1 over x. And then 4 minus 6, of course, is minus 2. Right? So there's our answer. That is f of g of x. Or I could also write that f composed with g at x. Right? Different symbolism, but it says the same exact thing as f of g of x. Okay, look at this next one. This, we're going to go the opposite direction, g of f of x. So what are we doing here? Here, what we're going to do is we're going to take all of the formula for f, and we're going to shove it into g, where it's expecting an input. So f is x squared minus 3x, so we're going to take that expression, and we're going to substitute that into g, where it's expecting an input, which is only this one place, the denominator of the first term. So what is that going to be? G of f of x is going to be 1 over, instead of x, the input here now is x squared minus 3x. So 1 over x squared minus 3x, but then I also have that plus 2 at the end. Okay? That's not too ugly. I might just kind of leave that as it is. If I wanted to make it one rational expression, combine the two terms, I could multiply that 2 by x squared minus 3x over x squared minus 3x. Okay, then that would become 1 over x squared minus 3x plus 2 times x squared minus 3x, or if I distribute that 2, plus 2x squared minus 6x over x squared minus 3x. Now that they have the same denominator, I can add those numerators. So this will be 2x squared minus 6x plus 1. Kind of writing that as standard order, over x squared minus 3x. Now when I have a rational expression like this, I might want to look and make sure to see if that rational expression can be reduced. So I might want to factor it and see if there's any factors that divide out. Now does that numerator factor? No, it doesn't. I'll just double check that. I've put on my calculator here, I've got a program on my calculator, I called it Quad. I have a program on my calculator to solve a quadratic equation for me, or to find the factors if there are any. I just have to tell it what the A, the leading coefficient, is. So that's a 2, A is 2, B is negative 6, and then enter that. C is positive 1, All right, so what do I have? Decimals. So it's not going to factor. Those are the solutions. If I were to set it equal to 0, they're the roots. But that just confirms I was looking at that and didn't think it factored anyway. Okay, so there it is. There's our composite function g of f of x. By the way, I do not mind if you want to, if you don't have it already, if you want to program, if you want to create a program in your calculator to solve quadratic equations. The quadratic formulas can be a nuisance, right? And in this class, I don't want you to have to do unnecessary calculations. So you can go ahead and program that into your calculator if you want. Now, probably the easiest thing to do is Google it. How to program your whatever calculator you particularly have. I'm using the TI-84 Plus. I'll show you what my program looks like. When I click the program key, I have 3 options. I can execute, edit, or create new. I did execute when I wanted to use my program to solve the quadratic equation. If I go over to edit, move over to edit and press enter, I can see what my program looks like. And I did. It's kind of hard to see. Get the glare out of there. There we go. And I did type this one in. I did this myself. And there are some programming. The programming here is very simple. It doesn't something to be intimidated by at all. But here's what my program looks like. You're welcome to use it. You can Google it. There are other similar ones, but it's really a very simple program. And to know how to enter the program, again, you can just Google that too, how to program your whatever model your calculator is. Okay. All right, so what else do we have here? Okay, the function, okay, so here we have some more examples. Let's look at these. The function p is defined as the cubed root of x squared minus 3. Okay, and we could express that in the form f of g of x, where g is going to be x squared minus 3. Okay, so this function p is a composite function. It is a composite function. What this example is doing is asking us to undo the composition, undo it, right? So if p of x was f of g of x, what would be the outside function and what would be the inside function? Now they've given you the inside function, right? So we have some help. They're saying the inside function g of x is x squared minus 3, right? There's the x squared minus 3. Well, what would f have to be, right? If its inside function, or if x was x squared minus 3, so they're saying what would f have to be if g of x was just x? Another way of thinking about that. Well, it would be what? What's left after I take that out? If I replace that inside function, that g of x with x, all I have is the cubed root of x. Okay? Here's an absolute value function, h of x. It's a composite function as well. It's a composite function as well. It's f of g of x, where g of x is our inside function, right? So we want to replace that inside function with x. Here they're telling us, look, they're saying, I don't know, find the inside function if the outside function is simply the absolute value of x, right? So the outside function is just the absolute value of x, right? What does the inside function have to be? Well, the inside function then, obviously, the inside function would have to be, what would the x have to be? It would be this guy right here, right? 3x plus 4. So we could say that g of x, the inside function, is 3x plus 4. Okay. A couple more comments here on composite functions. The domain of a composite function is interesting. It's interesting because you've got to consider any domain restrictions on the inside function as well as domain restrictions on the composition, right? So if f of x is 1 over x minus 8 and g of x is the square root of 2x, if I wanted to find the domain of f of g of x, right, I've got to consider any domain restriction of this inside function as well as any domain restriction of the composition. Now, do I need to worry about the domain restrictions of f of x? No, I don't. It will be covered It will be covered because when I compose them, remember the x gets replaced with g when I'm doing f of g of x. So as long as I address domain restrictions of g and my resulting composition, I'm good, right? So let's see. Let's go ahead and find out. In fact, yeah, let's go ahead and find out what f of g of x is. Let's find it. F of g of x means all of g becomes the input, or the x, in f of x. So that's going to be 1 over, instead of x, the square root of 2x, then minus 8. So there's our composition. There it is, our composed function. So to find the domain, there's two things I need to consider when I'm looking for the domain of composite functions. One, I need to consider exclusions. Let's write that up here. Consider domain exclusions of the composition, or the composed function, but then I also have to consider domain restrictions of the inside function, or the input function. Okay, domain restrictions of both I've got to consider. So here's my composition. I compose it. There's f of g of x. What domain restrictions do I have to address here? Well, I have a denominator with a variable in it, so I know that can't be 0, right? So first I'd have to say the square root of 2x minus 8 can't equal 0. All right, let's see what value of x makes it 0, and let's exclude it. All right, well, let's see, add 8 to both sides, so the square root of 2x can't equal 8. Square both sides, right? So 2x can't equal 64, and then divide by 2. So here's one domain restriction. X cannot equal 32. There's something that can't be in the domain. So again, remember with domain, we assume all real numbers. We assume all real numbers, and then we just remove from all real numbers any restrictions that we find. All right, so that's the composite function, but I've also got to address something else here. Look, my inside function, g of x, the square root of 2x, there it is. Could this, if this radicand, if 2x was negative, could that be in the domain? No. No, we cannot have negative radicands of even roots. We have to exclude that from the domain as well, right? So any value of x that made 2x negative, it can't be in there. So I'd have to say, let's see, 2x has to be, can it be 0? Yeah, that's fine, right? 2x has to be greater than or equal to 0. That's another thing I have to say. Divide both sides by 2, and we just have that x has to be greater than or equal to 0. All right? So what does my domain, oops, that's an O. What does my domain then have to be? Well, it can't be 32, but it also has to be greater than 0. So I'm thinking, if I think about my number line here, right, when I'm writing my domain, okay, if 0 is here, and 32 is there, right? Anything greater than or equal to 0 is fine. That'd be like a closed circle on the 0. But I've also got to exclude that 32, so I want to open circle right at 32. That's what the graph would look like. In interval notation, we would do this. We would say it's 0 all the way up to 32, but then use a parenthesis to say the interval needs to stop at the actual value of 32. But it can pick up again after 32. So in union with parenthesis 32 to infinity. Okay? So all values between 0 and 32, inclusive of the 0, as well as all values greater than 32, are adequate inputs to this function f of g of x. None of those values will result in a domain restriction. None of these values in this interval will result in a negative radicand of an even root, right? 2x won't be negative, or 0 denominator. 2x minus 8 won't equal 0. Let's try doing it the other direction. Let's see, that was f of g of x. Let me even switch pens here to a little bit different color. Let's do g of f of x in blue. Let's see. What is that going to be? G of f of x. Well, that means the formula for f of x or the algebraic representation of f of x, becomes the input to g, right? So everywhere that g is expecting an input, it's going to get f instead. So everywhere there's an x in g, it's going to get 1 over x minus 8. So f of g of x then is going to be the square root of 2 times 1 over x minus 8, right? I might simplify that and write that as the square root of 2 over x minus 8. 2 over x minus 8, right? Okay, so we got to think about domain restrictions here, right? Here's my composed function, right? That's an even radicand, that's a square root, right? We don't write that too, but that's a square root. So that's an even radicand, so that means this 2 over x minus 8 has to be greater than or equal to 0. 2 over x minus 8 has to be greater than or equal to 0. All right? That's an inequality, so I'm going to have to solve that. Now, when I solve that as an inequality, can I just multiply both sides by x minus 8? No, I can't do it like an equality, because if I do, what's going to happen to the x minus the x? It's just going to go away. 0 times x minus 0, and I would say 2 is greater than 0. Well, of course it is. It always is. But I want to find values of x that make 2 over x minus 8 greater than 0, right? So if I set the numerator and the denominator both equal to 0, that should give me some intervals. Well, I can't make 2, 0, right? I can make x minus 8, 0. Let's see. If x minus 8 is equal to 0, then x is 8, right? So here's why I'm going to figure this out. On the number line, I've got 2 intervals right at x equals 8. It's either going to be the interval of values less than 8, or the interval of values greater than 8, all right? Well, if we put any value less than 8 in here for x, what happens? 2 over x minus 8 becomes negative. Look, if I did 7, this would be 2 over negative 1, and it's negative, not greater than or equal to 0. So that means I can't have any values less than 8. I can't. Greater than 8, though, that's going to be fine. All right, greater than 8 is going to be fine, because 9 minus 8 is 1, so 2 over 1 is positive 2. Any value greater than 8 is going to work, right? So this portion greater than 8, including 8, it's fine, because we can have 0, right? Oh, no, we can't. Look, 8, but we can't divide by 0. So actually, that's going to be an open circle there, isn't it? When I look at the full problem, right? So far, it looks like I've got this interval of everything greater than 8 with an open circle. So parenthesis 8, get that on the screen, to infinity, okay? So there's my domain restriction. There's my domain, actually, for the composed function. But what about that inside function? Let's take a look at that. Did I already address that? Well, since the inside function, right, the function I'm composing into g is 1 over x minus 8, 8 is the value that needs to be excluded, right? I've already got it excluded because I noticed up here that I couldn't do it. So we're already good here. It can't be 8. So that's going to be my domain then is simply going to be 8 to infinity. All right? Okay, one more thing before we close out this lecture. Let's take a look at why we would have a composite function. Why do we even need composite functions? Does that actually happen in the world? Yeah. I mean, a lot of times we have 2 functions that work very nicely, but we want to use the input of one function as the output of the other. And we don't want to do those separately. We want to write it all as one function. We can do that, right? Let's look at this example here. Here we have a city manager. Okay, the city manager found that there's a function, R of P, that represents the amount of tax revenue brought in by the population of some city, okay, P. Now, when I'm reading through problems like this, I kind of like to write down, you know, when they're defining what things are, I kind of like to write them down and just kind of make sure I understand what's what. So the first thing they talk about in this is R of P. What is it? R of P, I think that's a function to find tax revenue. So we'll just call it revenue. Okay, and then they're also telling us that P is the population of the city. Okay, so I got that. Now, we go on and read, and it says it's also been found that the population can be determined using a function T of Y. right? And we estimate that population using some function t of y, where y is the number of years since 2010. Y is the number of years since 2010. All right, so let me write that down. So t of y is a function that gives us what? What does it give us? It gives us population, right? Let's see, t of y can be estimated. Okay, population is t of y. Okay, so, well, that's really interesting. I thought p was population. Well, it is. But t of y is a function to estimate population. I don't know what it is. And so then y is the number of years since 2010. Okay, I take the time to do this to make sure that I fully understand what everything is representing there. All right. Now, which of these tasks would be helpful in this situation? So if we wanted to estimate the tax revenue in 2019, right? Or even better yet, let's say we want to estimate the tax revenue in the year 2029, which hasn't occurred yet. So there's no way that we know what the population is in 2029, right? We don't know that. But we can estimate the population in 2029 using t of y, right? If we know the number of years since 2010, which we do, it's 9, right? So which one of these would work? So I would say process of elimination. Let's think about it. Would this first equation here, would this give us what we're looking for here? What are we looking for? We want to find tax revenue. We want to estimate tax revenue in 2029. So tax revenue. So this is going to R of something. R tells me revenue. Okay, so it's revenue. Okay, revenue. And as its input, we want to put t of y in population. Oh, that's revenue as a function of population. That sounds really good. But is it going to be equal to 9? No. 9 was the years since 2019. Or we'll change it to 19 since we made it some point in the future. 19. That's the number of years since 2010. Number of years since 2010. So no, that's not quite right, is it? So I don't want that. How about here? What if I want to solve t of r of p equals 19? Well, that's years again. But well, that is somehow, am I going to be able to solve for revenue here? Well, I don't know. What is t? Again, ty is population. Okay, population in years since 2019. No, y is the years since 2019, so that's not right either, because this 19 is the y, right? So there's something wrong with that. That one, I don't think that one's going to work either, right? How about this? Evaluate r of t of 9, right? Evaluate. Find the value of r when t of 9 is the input. R, well, that's what I was looking for, revenue, right? R of p. And look, t of 9, well, 19, because we changed it a little bit, right? T of 19 is population, right? So since p is population, t of y estimates population. I think this is the one that I want. I think that's going to give me a revenue estimate in the year 2029. Right? What about this last one? Just to make sure, evaluate t of r of 19. R of 19, well, revenue is expecting population as its input, not the number of years since 2010. So that one clearly is not it. Right? So here's what I want to do here. I would want to evaluate r of t of 19. Okay, t of 19 is a function that gives us population. Revenue needs population as its input. Why would I want this? Well, because if I want to estimate revenue in the future when I don't know the population, I need to use this function to estimate population, right? And I don't necessarily want to do two things. I can make that into one. I can make that into one function, all right? Okay, so this ends the lecture for section 1.4, composition of functions.